Hi, welcome to Qiskit course lesson number 3. Today we're going to use long-range CNOT gate for teleportation, and we're going to see what's a dynamic circuit. I'm just gonna leave the installation requirements here. You can set your own environment and also some of the libraries that we're going to use. Going directly to what's a dynamic circuit. Dynamic circuit is just as analogy to the real-time classical control in a classical computer. Notice that in the previous exercises that we have done, that's like an end-to-end process. You don't measure the qubits in any point of the circuit, just at the end to get the measurements, the shots. But here we're going to have the shots at any point of the circuit. And using that measurement, let's say at 0 or 1 from a qubit that we can have with some probability, we're going to be able to create conditional gates, to reset operations, to create a branching logic, and if else statements, and this is what is going to expand the process of the quantum computer. And we're going to work with quantum teleportation. Notice that I mentioned it as teleportation, not transportation, because from the physical perspective, we have never transporting or teleporting energy. Just it's a way that we process the information and is sent it in a particular way. So this is known as a protocol, and you're going to find this in applications for quantum cryptography and quantum information. The key idea is that you're going to have two sides of the protocol, which it's usually known as Alice and Bob. Alice and Bob share two qubits, which are entangled, and these qubits you're going to be able to, by measuring and creating a classical channel, communicate to Bob information about the qubit that he has without measuring it, because we can measure Alice's qubit, and with Alice's qubit we're going to get information from Bob's qubit even if he hasn't measured it. And the idea is that you're never going to transport any kind of energy or information faster than the speed of light, because all the time to both to get that information you need to send it through a classical channel. Okay, so that's why it's always teleportation, because we're not violating any physical rule. You can check more details on this. This is a classical example, and the common state that we can have, one of the Bell states, it's one of these ones, like 0011. Here I have some of the details, but I'm going to use this function, demonstrate dynamic circuit basics P2. Here I'm going to leave you 3 examples. As in the previous lesson you saw how to build the quantum circuit. Here we have in particular 2 qubits and 2 bits, 2 quantum bits and 2 classical bits. We set the operation rules, and also notice that the measurement that we have here, the extra measurement, is in the middle, as I said, because this is what's going to be the dynamic circuit. You can check here for more detail on how these examples are built, but I think it's more interesting here in visualizing the dynamic circuit. We can observe them. This method, visualize dynamic circuit, and visualize dynamic circuit simple, is just to print the structures in the circuits in a different rule. Remember that Qiskit can give you these visualizations. I just presented in 2 ways, with some of the parameters like the depth, number of operation, number of qubits, and number of classical bits. Check that we are going to have at the end 4 channels where this mid circuit is the most relevant to check right now. You have qubit 0 and qubit 1. qubit 0, remember that this is read from left to right, and then qubit 0 is going to be applied, the Hadamard gate is going to be applied to the qubit 0, Q0, and then you're going to have this C naught. And depending of this first process, we know that now we have a mixture of probabilities here, and then this operation, this first block of the Hadamard and the C naught is what creates an entangled pair. So right now, after this process, we have an entangled pair. This box that is the middle circle is the measurement. And what it means is that you're going to measure qubit 0, and depending on that result, you're going to get it to the channel, and that you're going to have it in your classical channel, and you're going to send it to the end of the process. You also can apply Hadamard again to recover like the first state that you had, and then you just measure qubit 1, and then you can have that information as well. But the idea is that you already send in the classical bit the information from the first qubit, so you already know what's gonna be the result at the end when arrives this bit, this classical bit at the end. And here with some examples in the conditional operator, imagine that you can have a general correction at the end. So you after you measure the qubit 0, you can check from in the process what's the value that you got, and depending on that you create an if, a condition to activate or not a gate and operate and create some correction. So in the same way, you can reset the operation, you can create different conditions, and then also create more complex sets. In this case, I'm just giving an example of the same case, but with 3 qubits. So depending on the result of the qubit 0 and the result of the qubit 1, you can activate or not two different conditions in this case that I'm using here, X gate and Z gate, and that's what's on top. Because we already discussed a bit on how to build these quantum dynamic quantum circuits, and the only difference with the ones that we already built is the measurement in the middle. I'm gonna leave it like that, but if you want to check how it's look the condition, check here that in this line of code is where after you have the measurement and the value stored like this, you get the conditional as using this with qc3.if test, and he's going to take the value depending on the shot that you made, and he's going to apply it or not the functions that you defined here, which I use is the X gate and the Z gate in this case. So going a bit further, to implement the quantum teleportation, you just need to define at least 3 qubits. So this protocol is going to be defined in this function create teleportation circuit, creates a complete quantum teleportation circuit using dynamic circuits, right? We're going to have qubit 0, qubit 1, and qubit 2. The first two, one is the Alice unknown state. This is the one that's gonna be teleport, and the second one is Alice half of Bell pair, and Bob's also having a half of the Bell pair. So we're going to have an entanglement, a pair of qubits, one for Alice, another one for Bob, and Alice has another qubit that she doesn't want to touch, because if she touch or she measures this qubit, is going to break it. So she wants to transport the information of the qubit without knowing it. And so Bob can guarantee that he has the same qubit at the end. And for that, then we create the dynamic circuit here. As the quantum circuit, we have 3 qubits and 2 classical bits. If we're going to do something like this, as this reset operation, and this correction that I mean is depending on the measurements of the first two, we can modify the second qubit, which is going to be the entangled pair from Bob's. So easily here you can check that we're going to create the dynamic circuit with 3 qubits, 2 classical bits, and then we're going to define a general rotation here p over 3 and p over 4 for theta and phi. Check here, I put superposition state that is going to represent. You can check this math all the time, that if you remember from the block sphere, you can always define these angles for a general qubit with a complex phase. So these rotations, you can have it from rotation around y axis and z axis, and these rotations are going to be like the general transformation that you can apply to any qubit, at least to transform it to other qubit, which is relevant. And well, first, in the first step, we create the Bell state. Usually to create a Bell state, you're always going to use a Hadamard gate on one and a CNOT gate on the other, on that qubit and the other one. So this is how you entangle this pair. So that's why I define it for 1 and 2. And the qubit 0, remember, is the unknown, the one that we want to teleport. And I put here, as you can see, the Bell state that is created. You can check which kind of Bell state if you do the math yourself, but here I just summarize it. It's going to be a 50% chances of being 0, 0, and a 50% chances of being 1, 1. And then Alice has qubit 0 and 1, and Bob has qubit 2. Remember that 0 is not entangled. Here this barrier is just for visual clarity in case you print the circuit. And then you're going to perform Bell measurement. For this, you're going to have a CNOT between the unknown state of an Alice Bell's qubit. And also you're going to apply a Hadamard to the unknown state qubit. So after you do that, you're going to have a measure of Alice qubits. You're going to measure qubit 0 and qubit 1. And you're going to store them into the 2 classical bits that you have into the classical bit 0 and the classical bit 1, depending, and you can have here any result 0 or 1 or 1, 1, 0, 0, 0, 1, any kind of combination. The idea is that the CNOT and the Hadamard are applied to the Bell measurement before, right? And then Alice qubits are stored into the classical bits. This is because now this information is sent to Bob, which has the second qubit, the one that is entangled, and he can apply a correction based on Alice measurement. And this is the dynamic control, because he's still on the protocol, he's still processing the qubit, and he's going to receive some classical information that's going to activate for him some of the operations. And then we decide to have these 2 corrections. If the classical bit 1 is equal to 1, then you're going to activating the X gate into Bob's qubit, and if the classical bit 0 is also 1, you're going to activate set. These both conditions can be satisfied at the same time, or just maybe one at a time can occur. But at the end, this, if you make the calculation, this is always going to transform Bob's qubit into the unknown state qubit, the first one, without knowing actually. You can just present this general state, which it's important then. If you present this general state and you check this operation, you notice that this is the way to copy this information into the other one. And it's just because we just destroy the qubits, we get some information, and with that information we can correct the entangled qubit, and then we have verification measurement, which is optional and that's going to be destroyed in the state. But for our case, it's just to check the results, right? Here I've summarized all the steps that's been done there. And if you check here in the testing teleportation protocol, we're going to use R simulator. This is going to create the simulation of the mid-circuit measurement support. Actually, this part is quite straightforward. You, as in the previous codes, you here just need to define the teleport circuit as the copy. You're going to copy the circuit. You're going to measure all with this function, and then you can run the simulation. Remember, the first one is to add the final measurement to see Bob's state. This is like the last step for the circuit. And to run the simulation, you can use test circuit and try it around any number of times. Let's here have 1000. And then you check job result and counts of the results. Here the results are going to be the last bit, which is Bob's final state. Here I leave you a sorted a 4 to check the first 2 bits of Alice measurements, the results, and also the last bit of Bob, so you can have the information of the 3 qubits. And then you have the second test, which is the theoretical calculation versus the actual probabilities. Remember that we have the math, that's the actual probabilities, and then the calculate theoretical way. Here I just define some probability theory. Remember that we have the cos theta over 2 and sin theta over 2 for the probability into the states. So at least as the coefficients of the states here. So the square of this and the square of this, the norm square in general, which is going to be cos square plus sin square equals 1, and that's going to be the probability. And then you can check this the parameters. Here I just have mainly a lot of prints, so you can observe and check that I'm just with this testing. You can observe the measurement results at different points. So you have in the one case 0, 0, 0 and pop 0, and this is a 19% of the chances. Then you have 1, 1, 1, and Bob has 1, and this is 6.8. And at the end, if you add up everything, you're going to get around 100%. And this theoretical versus measured state, then you can check the probabilities. Check that we are quite close. In the theoretical prediction, we have a 0.75 for state 0. And for the measure that we are measuring here, 0.71. Of course, if you increase the number of shots, these numbers are going to get closer. So at least with the teleportation fidelity estimated here, we have a 0.99 fidelity, which is great, and you can increase it by increasing the number of shots. In this moment, is not necessary. Well, and here just to mention the long-range CNOT gate implementation. The function to create a teleport CNOT circuit tackles the challenge of limited qubit connectivity. Why? On many real quantum devices, not all qubits are physically connected, so you cannot run CNOT between arbitrary qubits. But teleportation provides a way to move the logical control or target anywhere by relaying it through entangled pairs. So these implementations uses extra qubits to build a chain of entangled links. So each pair between distant qubits, and then you teleport the control state to an ancilla that's adjacent or it's in one side or closer to the target, making it possible to then apply a direct CNOT at the end point. Here I'm going to leave it more like an exercise, but the idea is that each teleportation uses dynamic correction logic as before. Hence, why understanding and verifying those dynamic circuit blocks is so crucial. And it's more like a practical demonstration of how quantum networks or error correction layouts can harness teleportation to overcome hardware limitations. But the idea that teleportation itself is the way that you're going to physically connect your system, at least in a first approach, to um, not touch your qubits, but still process the information to other qubits that maybe are you need to interact with. In this case, you can check it. You're going to have a control and the qubits that for Alice bridge Bob, the being Alice and Bob the ancilla qubits, and then the target qubit being the end. You're going just to see like a more general expansion. I leave it here for the ones that are interested, but also just to remark that I also gonna leave some of the analysis of the plots. This is homework for the one that wants to check this part on the fidelity of a larger state. The code is in the basis the same applications of Qiskit. Here we just include these middle measurement points, and as a real world extension, I'm just going to summarize here some of the points that you can check for building quantum networks, quantum error correction, quantum cloud computing, modular quantum architecture, and future prospects. Everything is going to be in the notebook. One detail to mention is that everything here, here in advanced dynamic circuit patterns, we're going to use this for quantum error correction in the next one. Remember that quantum error correction comes from the real hardware of the quantum computer, and then this information that we are losing or we're losing and that we also can get damaged or not well processed, then we also need to apply a correction. And this correction is also a dynamic circuit because we need to measure some stuff and some classical bits that allow us to decide to apply new operations, the corrections itself. Here I just leave and demonstrate an advanced dynamic pattern. You can check it, it's well commented. And thank you for paying attention to this one. I try to do this one a bit faster because the main idea of the protocol is just the dynamic circuit measuring in the middle. So with that detail, it's just what we have seen already, but with extra interpretation. You can check more in literature for what's teleportation, the process of Alice and Bob, and the different protocols that you can create. But all of them are going to be programmed in the same way that you have here. So thank you so much and see you in the next lesson.